Good morning and namaste. It's me, Lil Hamal, your science teacher. Well, I'm going to teach you grade 9 science. Okay, the chapter is work, energy, and power. Well, this is the distant program brought by Metro PABSON Bharatpur Chitwan and broadcasted by Kalika SD all over the world. Well, first of all, I would like to welcome you in my class. Let's welcome. Let me share my screen. Okay, have a look. Thank you. Distant teaching, Bharatpur Metro PABSON. Welcome, grade 9, science, 25th Asus, 2077. Well, so let's have a look. The chapter of this morning, grade 9, the chapter is work, energy, and power. Okay, good. So first of all, let's talk about some of the important terminologies used in this lesson. Okay, so I've got already written on the board. Have a look on the board. So work, positive work, negative work, zero work, energy, kinetic energy, potential energy, power, the horsepower. Okay, cool. Work. So what is work? Well, when a body is moved by a certain displacement after applying a force to it, that is called the work or work done. When a body is moved by some distance or displacement by applying the force in it, to it actually, it's called work. Work, W equal to force into displacement. So W equal to force into displacement or distance simply. W equal to F into S. So work also can be defined as the product of the force and displacement. Per your level, you can simply say distance. So W equal to F into S. Well, so we do different types of works. For example, we run, we climb, we throw the stones up. Sometimes we carry heavy loads on your heads and we walk. And likewise, we run, we climb a tower, and we do swimming, we do cycling. These all are work. And even sometimes we say we are working. For example, someone sitting on a table and working, and still we say work. But what type of work are they in science, in physics? So work means that should be application of a force on a body, and that body should be displaced by a certain displacement distance. So there should be application of the force and the body should be moved by a certain distance. Then after there will be work done. But sometimes the work done can happen actually, and sometimes the work done does not happen actually, and sometimes the work done will be just negative. So why and how? Okay, have a look. So on the basis of that, there are three types of work: positive work, negative work, and zero work, or work not done. Work not done. Okay. So when the value of work done is positive, that is called positive work or positive work done. Okay. So for that, the force applied and the distance should be positive, or displacement should be positive. So it gives the positive work. Sometimes the work is whether positive or negative. We need to think about the angle applied to it. We will go through that in detail later on in the topic, the work, especially during this session. So now I'm just going to talk about what is simply the positive work. The work is done, positive. The value of work done that we calculate and we find is positive. So it's a positive work done. The value of F and value of S is positive, so that the product of F and S is positive. So negative work done. Negative work done. So because of some negative work done. Negative work done means the work is done actually against the direction of the direction of your force applied. For example, you are pushing a truck upward, but actually the truck is pulling downward because of the gravity. The work done here is the gravity. By the gravity is the negative work done. So actually you are trying to push a truck upward, but the truck actually the coming downward or pulling downward because of the gravity. That's the negative work done. So likewise, when you pull or push something, the work done by you, for example, you pulling a cart or you pushing a cart, that's a positive work. But the friction is applying in the opposite direction of your force applied. That is the negative work done here. The work done by you while pushing a cart is positive work or positive work done, and the work done by the negative in the opposite direction is a negative work done. Well, zero work done or work not done. So what does it mean? Some people say, for example, one student sitting on a table and reading like 10 books on a day and preparing for exams and reading hundreds and thousands of the pages. So in general speaking, we say he is working hard. He is working. But in science, he hasn't done any work. So that is called zero work done or work not done. Because to be work done in physics, the value of effort or force and displacement should be the positive. There should be some sort of value. But while someone is sitting tens of the hours and reading a lot of books, he may provide a lot of work or pressure on the brain, but he is not. He is not moving, means he is not covering any distance. It means the S equal to 0. So F into S equal to 0 work done. Or let's talk about something. For example, I'm trying to push a wall. For example, the board, when I push and I'm unsuccessful to push this wall or the board, or let's say truck. So I applied a lot of force, like 1,000 Newton, but I made the truck or wall to be displaced by 0 meter. F into 0 equal to 0 work done. So 0 work done is actually the work is not done, whether because of the value of F is 0 or because of the value of S is 0. That's why the work is not done. Work done equal to 0. Energy, the capacity to do work is called energy. So mechanical energy is of two types. One, kinetic energy, the energy possessed by a body because of its motion. For example, the energy present in a flying aeroplane or moving car, rolling stone, flowing river, the blowing wind, that sort of energy are the kinetic energy. Okay. Likewise, the energy present in the molecules of boiling water, that's a kinetic energy. Potential energy means the energy possessed by a body because of its position. For example, something is kept at a certain height and it has got some sort of energy. So that is called potential energy. Next one, the power. The power is the rate of doing work is called power, and horsepower. So before, in ancient time, people used to say horse has got a lot of power. That it obviously happens. One horse has got different power than that of another horse. But people thought that a healthy horse has got some sort of power to pull like a cart or chariot or this is something, you know. Actually, people used to use the horse as the means of transport. And the power of a horse is equal to 1 horsepower. It is equal to 746 watt. 746 watt. Okay. So these are some of the terminologies in the beginning of the session to make familiar about work, energy, and power. Pretty much these things we have been done in grade 8 as well. Now I just did it. Let's go to the lesson. Okay. So let me share my screen. Well, what is the work? Okay. So let's start the work. It is said to be work done or work when a body is moved by applying some force in the direction of force applied. There is a body and you apply the force to that body. And that body moved in the same direction in which direction you are applying the force. For example, you are pushing, means you are applying the force in forward direction and that body moved in the forward direction. And now you apply the force, there is some amount of force applied and the body moved covering some distance. Now it is said to be work done. So what is the formula of work done? The formula of work done is the force multiplied by the displacement, force into displacement, or W equal to F into S. What is the unit of work? The SI unit is joule, J, and CGS unit is erg. So actually the joule is the multiplication of Newton and meter. When there is Newton meter and it is equal to the joule, J. So 1 joule equal to 10 to the power 7 erg. What is the relation between erg, the CGS unit of the work, and the joule, the SI unit? 1J equal to 10 to the power 7 erg, ERG, erg. What is the SI unit of work? Joule. And what is the CGS unit of the work? Erg, ERG. So what is the relation between joule and erg? 1J equal to 10 to the power 7 erg. That is the answer. Done. Okay, so let me derive the relation between the joule and erg. Okay. Relation between J and erg, joule. So what is the relation? 1J equal to 10 to the power 7 erg. Joule is the SI unit of the work and erg is the CGS unit of the work. So let me prove this. We know that work W equal to F into S. 1J equal to force should be 1 Newton, distance should be 1 meter. Okay, so 1 joule equal to 1 meter, 1 Newton, 1 meter, or 1 into 1 Newton meter, 1 Newton meter. So we need to convert these things in the CGS unit. What is the CGS unit of the SI unit of the force? Newton. And what is its CGS unit? Its CGS unit is the dyne. 1 Newton equal to 10 to the power 5 dyne. And 1 meter, we need to convert, the meter is SI unit, we need to convert it in the CGS unit. 1 meter equal to 100 centimeter. So this is 10 to the power 5 and this is 10 to the power 2, dyne and centimeter, dyne centimeter. So 10, 5 plus 2, 7, 10 to the power 7, dyne into centimeter, that is the erg. So 1J equal to 10 to the power 7 erg. So that is the derivation of the relation between joule and erg. So we came to know 1 joule equal to 10 to the power 7 erg. So it's how to prove 1J equal to 10 to the power 7 erg. So J is the SI unit and org is the CGS unit. We know W work equal to force into displacement. W, let's say 1J, 1 into 1, 1 Newton, 1 force, 1 Newton, displacement 1 meter. And 1 Newton is equal to 10 to the power 5 dyne, because the CGS unit of force is the dyne. 1 Newton, the relation between Newton and dyne is 1 Newton equal to 10 to the power 5 dyne. You need to memorize this one. And 1 meter equal to 100 centimeter. 10 to the power 5 into 100 means 10 to the power 2 dyne centimeter. So 10 to the power 7 org. So 1J equal to 10 to the power 7 org. So the same thing given on my screen as well. Have a look. W equal to F into S, 1J equal to 1 m 1 meter, 1 Newton 1 meter, 1J equal to 10 to the power 5 dyne into 100 centimeter, and this and this and this. Therefore, 1J equal to 10 to the power 7 org. That's done. Okay, so examples of work done. There are some of the things that we do and that we say the work done. Okay, what are some examples of work done? I cannot list all the examples of work done, but some of the examples of work done. Running, the walking, cycling, climbing a staircase or climbing a tower, climbing a tree, swimming, boating, driving, pushing or pulling a cart, okay, and many more. The pushing a car, a pulling a car. Okay, so these are some examples of the work done. And examples of work not done or zero work done. Sometimes we may hear about the someone is not the working. But what is meant by not working in science? The product of force applied and distance should be equal to 0. In that condition, it is said to be work not done or zero work done. Here, either F or S or both should be 0 to get the result of zero work done. So W equal to F into S. So to get the value of W, you must have got F equal to 0 or S equal to 0, or both of them should be equal to 0. Well, so some examples, so you can keep on reading the screen. So number 1, pushing a wall, but it makes your wall not moved. Someone tried to push a wall, but the wall did not move. Here, the distance covered is 0. We know that work done W equal to F into S, and if the value of S is 0, then after W equal to 0. The pulling a truck by using muscles, for example, simply I'm trying to say a man cannot the pull a truck because the truck is too heavy. And truck not moving means not displaced. It means F into S, S equal to 0 and 0. Sitting and reading. So one student sitting on a chair and reading for 10 hours, so work not done. Next one, the watching TV, sitting and watching TV, work not done. Standing, a security guard at a gate, a security guard is standing at a gate. And we say he is working, but science doesn't say he is working. Science say he is not working. Likewise, a man just standing and carrying a heavy load on his head. Standing, a man is standing and carrying a very heavy load like this. So very heavy load here, and he may be just standing, or he may be just walking even, not working. Okay, so not working because the value of W becomes equal to 0. That is why not working. Okay, so these are some examples of work not done. So, so let me share my screen. So what do you mean by 1 joule work? What do you mean by 1 joule work? So 1 joule work can be defined as work is said to be 1 joule, or work done is said to be 1 joule if a body is displaced in the direction of force by 1 meter by using 1 Newton force. Okay, so we know that W equal to F into S, or W equal to 1 Newton and 1 meter. W equal to 1 Nm, Nm is equal to J, means joule. Therefore, W equal to 1J. So, 1 joule work, let me derive here. 1 joule work, what does it mean? So, W equal to force into displacement. So have a look. If the force is 1 Newton and displacement or distance is 1 meter, 1 into 1 Newton meter 1 J. So work done is said to be 1 J when a body is moved by 1 meter by applying 1 Newton force. You can say in any way, but do not forget to say 1 Newton and 1 meter. When 1 Newton force is applied to a body, this is a body, and the force is applied to that body. How much force? 1 Newton. This body moves from A to B position, and the total distance traveled by this body is 1 meter. And what is the total work done by that person at that instance? So it is equal to 1 joule. The work done is said to be 1 joule when a body is moved by 1 meter by applying or after applying 1 Newton force to it. So this is a very important question. So define 1 joule work. Work done is said to be 1 joule if 1 Newton force is applied to a body and it is moved by 1 meter. Next one, have a look. Nature of the work. So in the beginning, as I talked about the natures of the work or types of the work, so on the basis of that, I'm going to talk about again a positive work, negative work, and zero work. Positive work, negative work, and zero work. Okay, the actual formula of work done, W equal to F cos theta into displacement. Yes, the actual work done, W, the actual formula of work done is F means force cos theta into S. So though we are applying a lot of force and the angle of the force applied tells or determines what type of work we have done. So let's talk about when theta is less than 90, when theta means angle is equal to 90, and when theta is greater than 90 degree. Okay. So let's talk about what happens when the value of cos theta. So theta means an angle when the force is applied to a body with an angle less than 90 degree. So we get positive work. We get positive work because the value of cos theta, the angle of cos, is positive up to 90 degree. Below 90 degree, I beg your pardon, below 90 degree is positive. And when theta equal to 90 degree, the value of cos 90 is 0, and we get 0 work done. So when we apply the force to a body less than 90 degree and we push or pull or something, what do we do? And the total work done is positive work done. For example, pushing a cart, pulling a cart, or cycling or walking. These are the examples of positive work. When theta is 90 degree and we say 0 work done. For example, someone handling a briefcase and walking through the platform, and he looks like he is working very hard and carrying a heavy case, but the angle of that briefcase, let's say the weight, the gravity is totally 90 degree to the ground, and the value of 90 degree, cos 90 degree is 0. That's why it becomes force, let's say 1000 Newton into 0 into something, and we get a value 0 overall. That's why when the force is applied at 90 degree, then after it is said to be 0 work done. And sometimes if the angle is the greater than the 90 degree, the the value of cos is negative, that's why we get negative work done. Negative work done. So here the value of cos 180 is -1. So when we throw something upward, and the work done will be negative or against the gravity, and that is called negative work done. Okay, so that is the case. We get a positive work done when the force applied is at the angle of less than 90 degree acute angle. When the force applied is at 90 degree, that will be 0 work done. The right angle, when the force is applied in the angle greater than 90 degree obtuse angle, that's a negative work done. So have a look on my screen here. Okay, the actual formula to calculate work done, W equal to F cos theta into S. Depending on the angle of force applied, the nature of the work can be divided into 3 categories. Positive work, when theta is less than 90 degree, for example, pulling a cart or pushing a bicycle. Negative work done when angle is, the force applied to the angle greater than 90 degree. Example, throwing a stone vertically upward, negative work done. And 0 work done when the value of angle theta is 90 degree, because we have got the value cos 90 equal to 0. So a person carrying a briefcase moving horizontally or carrying a heavy load on his head, he has got the 0 work done. So nature of work done depending upon the angle on which the force is applied. These are some examples. Okay, you can give the example of positive work done, negative work done, 0 work done. Okay, that is the way. Now, types of work done. There are 2 types of work done against the friction. When we push or pull something, that work done is called work done against the friction. For example, cycling, or pushing or pulling a cart, or pushing a push bike, bicycle. These are some of the examples of work done against the friction. Next one, work done against the gravity means says lifting a stone or throwing a ball upward. The work is done in the opposite direction of the gravity. That is called the work done against the gravity. When the work is done in the opposite direction of the friction, that is work done against friction. When the work is done in the opposite direction of the gravity, that is called work done against gravity. Against means in the opposite. So work done against friction. In this condition, the formula is W equal to F into S. And the work done against gravity, we throw something upward or we lift something upward. W equal to, this is the M, means mass of that body, acceleration due to gravity, small g, 9.8 for the earth, on the earth, and h, that is the height of something. So for example, I threw a ball of mass 2 kg in the upward up to the height 10 meter. So m, so 2g 9.8 and 10 meter into 10. So what I get, and that will be the total work done. Okay, so good. Okay, I've got some numerical problems. Quickly have a look at these numerical problems, and we'll be doing these numerical problems. Calculate the total work done when 10 Newton forces applied to a body and displaced by 10 meter. Okay, numerical problems. So you looked the question and have a look at the calculation. Okay, done. Thank you. Have a look on the board. Okay, so here is force solution. Here, F equal to 10 Newton. And let's say you can say distance, displacement, no problem. We treat the same in this instance, 10 meter. The work done, W equal to what? We know that W equal to F into S, or W equal to 10 meter into, I beg your pardon, 10 Newton into 10 meter, or W equal to 100 J. Hence, total work done is 100 J. So, this is the solution of question number 1. Similarly, have a look at the question number 2. So, have a look on my screen. Question number 2. Mona Lisa has got her body weight, I beg your pardon, body mass 30 kg, and she climbed a tower of 20 meter height. Calculate the total work done by her at that instance. So, there is given acceleration due to gravity is 9.8 meter per second square. Okay, so make sure you understood the question. Okay, so question number 2, solution. Here, so Mona Lisa has got her body mass 30 kg, and she has got the mass 30 kg, and she climbed the tower of 20 meter height. Height H equal to 20 meter, acceleration due to gravity G equal to 9.8 meter per second square. Work done W equal to what? We know that W equal to, in that instance, mgh, 30 into 9.8 into what? 20. So, what do you get the value? This is the answer. Just use a calculator. Very simple. So, 20, so is there something? 30 into 9.8 into 20, 30. Okay, so what you get, if you do the calculation, you will get 5,880. 5,880 joule answer. Question number 3. This is the last question for today. So have a look at the screen. So Kohinoor carried 10 blocks, each having 20 Newton weight, and shifted by 50 meter. What is the total work done by her at that instance? Her body weight is not in the matter of consideration at the moment. We are just considering the blocks. Okay. So question number 3. Solution. So total force F equal to, so one block has got 20 Newton and she has got 10 blocks, 200 Newton total force. And distance or displacement 50 meter. So work done W equal to what? We know that W equal to F into S, very easy. F 200 and yes 50, 5 to the 10, 5 to the 10, 1, 2, 3. Hence, total work done is this. That's all. These are some important questions. Have a look. So thank you. So thank you. That's all for today, and you have a good day. Stay home, stay safe. Okay, bye. See you tomorrow. We'll be talking about energy in tomorrow's class. Thank you very much.